Our next speaker for today is Dr. Fatwa Abdi from Zentrum Institute in Berlin. His main focus in research is also very of much interest for the solar to chem community, as his focus is mainly on developing photoelectrodes based on oxides, on oxide materials, and also a very important word that we need to consider and will draw a lot of interest during this presentation will be the word scale up. So thank you very much, Dr. Abdi, for being part of today's event, and the audience is all yours.
Oh, thank you very much. Could you confirm that my voice is audible and my screen is shared properly? Oh yeah, I see
it's
it
fine.
now. Okay, good.
We can hear you properly, and the screen sharing is completely fine.
Okay, good. Good morning, everyone. Thank you very much for the kind introduction, and also I thank the Solar to Chem team for the kind invitations. I apologize for not being able to be there physically, but I hope the online format would still be useful. So as mentioned, I work at the Institute for Solar Fuels, Helmholtz-Zentrum Berlin. We work mostly on solar water splitting, and I'd like to share a little bit about our activities today. And it's nice to follow Adelio, because Adelio already made some arguments regarding the advantages of photoelectrochemistry, right? So we don't have to do it again in my talk. So I begin with this little introduction on the current state of the art on solar water splitting devices. Adelio presented a similar plot. That this one was taken from a relatively recent paper that looks at the devices within the last decade or so. And from this plot, we can learn a couple of things. First of all, solar to hydrogen efficiency as high as 30% has actually been reported with the combinations of the PV and electrolyzer. And if you consider the integrated PC, we have also pretty high solar to hydrogen efficiency of very close to 20%. The other thing that we can take a look here is that if you take a look at the solar to hydrogen efficiency 10% line, above that line, most of the devices are actually based on 3,5 semiconductors. If you take a look above 15%, then exclusively all the devices are based on 3,5 semiconductor. And I think it is one can argue whether this is scalable or not. I think Sophia later will probably talk about that as well. But on the other hand of the spectrum here, we have oxide-based devices, which is arguably as well more scalable. We saw significant progress at the beginning, but the reported solar to hydrogen efficiency has been stagnated for a little while now, for a few years. And this is caused by material limitation because, for example, bismuth vanadate, one of the materials that's used a lot in these demonstrator devices, actually already hit the limitation. So the performance is already very close to the theoretical limit. That suggests that we actually need novel complex oxide, if you want to push this type of devices further, the performance. And indeed, that is actually what we are also working on in our institute and in my group. But this is not what I'm going to discuss today. Hopefully, in another opportunity, we can talk about this. From the same review, we have another plot, just different way of representing the data. Now the solar to hydrogen efficiency is plotted as a function of the absorber size. And from this, we can see that most devices, or a majority of devices, are based on small area absorbers. But like Adelio mentioned, larger area devices also start to be studied in the recent years. And the other thing that we can take a look here is that bear in mind that this is logarithmic, right? So larger area devices tend to deliver lower solar to hydrogen efficiency. And the situations is such that if you take a look at the top right-hand corner of this plot, we do not have any demonstrations that devices that shows more than 10% solar to hydrogen efficiency and an area larger than 10 square centimeter. Sophia and I recently also summarizes this in a slightly different format in this plot, which hopefully is going to come out soon. So the size of the plot here is the area in logarithmic scale, and as you can see, the larger data points over here tends to show also lower solar to hydrogen efficiency devices. So that raises the questions, right? What are the sources of the scale-up related losses, and how can we actually overcome them? Our interest in this topic begins with this spec demo project, which also with Afner and Adelio, as Adelio mentioned. So we have a goal of to scale up our photoelectrodes, and for us, it's our bismuth vanadate photoanodes. So EB and Yimeng were postdocs in the project, and we wanted to increase the area of our bismuth vanadate photoanodes up to 50 square centimeter. And as soon as we did that, the IV curve is shown over here under AM1.5 illuminations. So we decrease the photocurrent significantly when we go to 50 square centimeter. In fact, there we only have about a third of the photocurrent that we have in the small scale. The question is, of course, what causes this decrease? And one initial thought is that this inhomogeneous deposition process, we prepared this with spray pyrolysis, but scaling it up, scaling our process from the small scale to large scale may actually introduce some inhomogeneity. In order to test that, we took two different small pieces from this large sample, one from the center and the other one from the edge, and we measure the photocurrent voltage curves, and it turns out that when you actually take them in a small area, they're actually performing pretty well. It's doing the same as the small area equivalent. That means that our deposition process is fine, and this loss comes from factors other than the bismuth vanadate. In order to understand that further, we collaborate with Sophia and develop the two-dimensional model, a simple two-dimensional model. Since bismuth vanadate is not the problem, we take it out of the equation. So we really replace this with just the anode and the cathode. And we took a simple membraneless configuration that's reported also in the literature, where a hydrodynamics control of the electrolyte is used to ensure product separation. The detailed parameters can be found down here. We assume no bubble formations and further in the paper. The main conclusions or the results is shown here, where we plot the voltage loss as a function of the electrode size. And as you can see, the voltage loss increases as we increase the electrode size. And we can distribute that to different contributions to the substrate ohmic loss, pH gradient, and electrolyte ohmic loss. In case of the substrate ohmic loss, we can minimize this by replacing the FTO substrate with high conductivity substrates, like the ones that also Adelio mentioned towards the end of his talk, or add some metallic lines or bus bars like it's done in the photovoltaics community. In terms of the electrolyte ohmic loss, we can minimize the ionic transport pathway or increase the conductivity by concentration, right? What about pH gradient? So one solution is, of course, to introduce convection, and we would therefore like to understand how to actually optimize this. In order to do that, we first did an experiment to really monitor whether how severe is the pH change happening. We did this by simple experiment where we took this fluorescent sensor foil that is sensitive to pH, and we just dip it. We put it in between the anode and the cathode, and we monitor the fluorescence signal. This fluorescent sensor foil is sensitive between pH 5.5 and 8.5, so it's ideal for our neutral electrolyte water splitting with bismuth vanadate. So with this experiment, we continuously monitor the pH change between the anode and the cathode. So the results is shown here. So this is a work by Kesuke, who was a former postdoc in my group. Now he's an assistant professor in Tokyo. First we look at an unbuffered electrolyte just to make sure that we actually see clearly the pH change. And the color map over here shows the change of delta pH. At the anode side, we see that the electrodes becomes more acidified, whereas at the cathode side, the electrolyte becomes more alkaline. And the pH change is so severe that even away from the electrode over here, we also have a really big pH change. Now, if we compare that with the case where buffer is introduced, a phosphate buffer, we can see that the pH gradient also appears, but it's minimized. It's constrained to within 1 millimeter away from the electrodes, and it stabilizes after about 3 minutes. The other thing that we can see from this experiment is that we see a clockwise motions of the electrolyte, right? So it's clearer here in the case of unbuffer, but also in the buffer case, you see that the top part here becomes more acidified, and at the bottom here it becomes more alkaline. So what causes this motion? One possible explanation is the change in local electrolyte density. So our bulk buffer has a density of indicated with this purple point, and as the cathode becomes more alkaline, then it actually moves towards this direction, so it becomes heavier. So it explains why this electrolyte actually goes down, this part close to the cathode. But at the anode side, is it becomes more acidified, it becomes lighter. So it explains why it goes up. In order to confirm this explanations, we updated our multiphysics model to include this effect of local electrolyte density to trigger the buoyancy effect in fluid dynamics. And the result is shown over here. This is the velocity profile as we perform electrochemical measurement or electrochemical water splitting. And indeed, the velocity profile of a clockwise motions is also demonstrated here. And the measured, the simulated value actually is in reasonable agreement with the measured value. So we also measured the velocity of the electrolyte. We can also see strong convection close to the electrode because of this movement, because this movement is caused by electrochemical processes. And this is important because this is the region where we have this pH gradient. The importance of buoyancy is shown over here, or this buoyancy effect is shown over here, where we compare the measured delta pH with the simulation. So when we consider no buoyancy effect, the simulation results in this black dash line, and we overestimate significantly the pH gradient. We can only resolve the experimental data when we introduce buoyancy effect to our simulation. So this suggests that we also need to consider this further. Now, what about the impact of bubbles? So the experiments or the simulations that I showed did not consider any bubble formation. We improved that by introducing this Euler-Euler multiphase fluid dynamics and introducing bubbles in our system. We take the same level of current density, but the bubble formation efficiency and diameter is assumed to be constant from an experimental report in the literature. The results is shown here. So this is the color map of the velocity profile from the inlet here to the outlet. And as you can, if you notice, the velocity of the electrolyte close to the electrode is increasing along the channel of the cell. This is even clearer probably if we take a profile along the y-axis, which is shown over here, and going from the entrance at y=0, we see a typical parabolic laminar profile, and along the electrodes we see an increase of velocity due to this bubble liquid interaction. This velocity at this region, the velocity at this region, it turns out to be not affected by the inlet velocity, i.e., this bubble liquid interaction dominates is the dominant factor causing the velocity at this region. This is of course important because again, this is where the pH gradient is formed. So we then compare how this bubble-induced convection affect the pH gradient. First, in the case where no bubble formations is considered, we have a certain amount of pH gradient that decreases with increasing inlet velocity or forced convection. But when we introduce a bubble formation, we suppress the pH gradient significantly, and we no longer see the effect of inlet velocity. So it's dominated by this bubble-induced convection. So this is a positive aspect from this gas bubbles. However, at the same time, we also need to notice that the bubbles also introduce additional overpotential. One of it is due to surface coverage, and one can estimate the surface coverage from this empirical relationship reported by Vogt and calculate the overpotential caused by this coverage. We plotted here the bubble coverage from this simple equation as a function of the applied current density, and then we can compare the overpotential, which is the negative effect of bubbles here, versus the positive effect of bubble, which is the suppressions of pH gradient as mentioned here. So this simple analysis shows that above a certain current density, the positive effect of bubbles outweighs the negative effect. So future for different configurations, of course, this analysis needs to be done. And of course, we need to optimize this in a way that the positive effect would overcome the negative effect. Also note that here we only consider the two factors of bubbles, but other factors such as the ohmic losses, optical losses also need to be considered. All right, I'll speed up a little bit. So I'll switch on to, so far we look at the effect on the performance, right, over potential, but what about crossover? And this is especially important since any solar water splitting devices would need to be oriented towards the direction of illumination, right? And this is the same for photovoltaic, and it depends on the geographical location. And for us at the northern hemisphere, probably it would be around 30 to 45 degree. And now what happens to the product crossover? We show over here the bubble plume distributions or the gas volume fraction as a function of the angle, orientation angle. Of course, under vertical configurations, bubble stays very close to the electrode, and as we tilt towards horizontal, the bubble plume moves away towards the other side, and crossover can actually be exaggerated. The results is summarized here as a crossover as a function of the angle, and of course the crossover increases as device is tilted towards more horizontal orientation. And if we look at what contributes to this crossover, we can distinguish it to dissolve oxygen and oxygen bubble, or either dissolve oxygen or hydrogen, right? But here we see that if you have the cell width larger than 5 millimeter, you can actually minimize the crossover due to dissolved gases, and only gas bubbles contribute to the crossover. How can we overcome that? This initially we considered membraneless configurations, but of course membrane is one way to block this bubbles from moving to the other side. But in the case of putting a membrane or separator in a solar water splitting device, another considerations has to be put. Some designs that are out there requires that the illumination pathway requires the membrane or the separator to be placed in the illumination pathways. And if that is the case, we actually need to have a transparent separators. This is why we then try to look at several polymer sheets, for example, FEP and Mylar, and see whether we can actually make use of them, introduce porosity, and see how it performs as a separator. The transmittance of these two films are shown over here and compared against an anionic exchange membrane. And as you can see, it's actually performing better, especially the FEP over here, which shows more than 90% transmissions across the entire spectrum. And using this tool, we then, Siller, a postdoc in my group, we collaborated with our colleague at Braunschweig, where they then laser drilled this porous, polymer sheets to introduce the porosity. So we can tune, therefore, our pore diameters, the pitch length, and the porosity, as well as the thickness of the separator. And we investigated, using experiments and simulations, the impact of this separator properties. First, it's shown here the separator resistance, right, or the ohmic loss. The simulations and experiments agrees pretty well as a function of thickness as well as porosity, and the ohmic loss is shown to be lower than what we get with an anionic exchange membrane. So the ohmic loss is one factor. The other factor is, of course, the crossover. How well does this porous separators reduce the crossover? So we did a particle tracing simulations. I'm not sure how clear it is on your screen, but with this video, but I also put the snapshots here to illustrate the timestamp of different conditions, right? We quantify the bubble crossover and change the separator properties with this particle tracing simulation. Parameter investigations was done as shown over here as a function of porosity and pore diameters, which we validated with experiment. And the important things from this is that the analysis will be able to tell us what are the required porosity and pore diameters for safe operations. To summarize the ohmic loss, the impact on ohmic loss and crossover, we have this plot over here where we see the efficiency loss as a function of porosity. Of course, with increasing porosity, ohmic losses shown in red decreases, right? So we have lower and lower ohmic loss when we have more porosity, but at the same time, we have a competing effect of crossover, right? So this competing effect needs to be counterbalanced in order to, and compromise in order to arrive at the minimum efficiency loss. For this particular case of pore diameters of 400 micron, we see that a 25% porosity, for example, results in minimum efficiency loss. With that, in the last about 10 minutes of my talk, I'd like to switch gear a little bit and start to talk step back, right? So let's say we can, I've been talking about how we can, what are the sources of the scale-up related losses. But let's say if we have this large-scale solar water splitting, the question is whether it is competitive, right? So we took a look at several technoeconomic studies, right, which is listed over here. More are available, and which has looked at different configurations of photoelectrochemical water splitting. But most of them, or majority of them, have estimated the levelized cost of hydrogen, or LCOH, of about $10 per kilogram. The number varies a little bit, but I would say this is somewhat the average value. This is, of course, still pretty high if you compare it with the hydrogen from steam methane reforming, which is about $1.4, or from biomass gasifications, which is about $3 per kilogram. The technoeconomic analysis also tells us that if you compare PEC and PV electrolyzer, we have similar LCOH, and the solar to hydrogen efficiency is always the most sensitive parameter in their sensitivity analysis. But even when the solar to hydrogen efficiency is close to I mean, is 25%, which is very high, it's still expected to not compete with the fossil fuel based hydrogen, which is the steam methane reform hydrogen. Other study, for example, from the FCH Observatory of the European Commissions, also look at the possibility to couple grid electricity driven by PV or wind with electrolyzer, but the number also still does not compete with these fossil fuel approaches. Arguably, this will continue to decrease with the decreasing renewable energy costs, or even the implication, the implementations of carbon tax. But we're wondering if there's another strategy to increase the competitiveness. One way is to introduce coupled reaction, right? So if we consider a schematic over here where we have a tandem configurations, photoanode and photocathode, at the anode side, we produce oxygen, and at the cathode side, we produce hydrogen. The green hydrogen that we produce here is, of course, what we want, but the oxygen is abundant and low value, right? It's about 3 cents per kilogram. One way to increase the competitiveness is, of course, to replace this reaction with reactions that has a higher value added products. Alternative oxidation reactions have been considered in the literature. I highlight here a perspective by Kevin, but there are also other studies out there that looks at glycerol oxidation, FDCA, hydrogen peroxide production, for example. But what about at the catalyte side? What can actually we do at this side in order to increase the competitiveness of green hydrogen? Here, we propose to couple this hydrogen production with hydrogenation reaction of hydrogenations of chemicals. The process goes as follows. So we use the same electrode, photocathode, in order to produce hydrogen. Some of them will then be collected as hydrogen bubbles. But if we can take this dissolved hydrogen and utilize them in a hydrogenation reaction, we can then hydrogenate a chemical product or a substrate and transform it into a higher value product. This reaction is shown over here, itaconic acid hydrogenations to methylsuccinic acid as an example. The itaconic acid, because we can actually do this experiment in, we can do this reaction under atmospheric pressure. Itaconic acid is one of the platform chemicals, is one of the top sugar-derived building blocks, like also glycerol or this FDCA. And if you put hydrogen, if you add hydrogen to this itaconic acid, it will form methylsuccinic acid, which is an important solvent and feedstock in polymer manufacturing as well as cosmetic manufacturing. So this is definitely higher value chemicals in comparison to oxygen or even hydrogen, right? So in order to test this coupled concept, we performed the experiment by first electrochemistry, simple reactions. We just have the anolyte and the catholyte separated by by a membrane. At the anolyte, we have a potassium phosphate buffer because we're just going to do water oxidations in this case. We're not worried about that at the moment. But at the catholyte side, we have a phosphate buffer filled with itaconic acid as the substrate and rhodium catalyst as the hydrogenation catalyst in homogeneous form. And Keisuke did this experiment, and first we did it in dark electrochemistry with just platinum electrode as a proof of concept. And we did see in this plot the produced MSA, continuous production of MSA as a function of time, even with different flow flow velocity. So the hydrogen to MSA conversion efficiency can also be quantified, i.e. how much of the hydrogen that you produce are actually used for the hydrogenation reaction, right? So we obtain conversion efficiency as high as 60%, demonstrate this through this coupled approach. And I don't have time to show the proof here, but we show in our study that this reactions is happen through the coupled concept. So really, we form first the hydrogen, and then the hydrogen that is produced in situ used to hydrogenate the itaconic acid. So we did not hydrogenate itaconic acid directly on the surface of the electrode. Since we couldn't do this in the dark, we could also do this under solar-driven experiments. So we used the photoelectrochemical configurations as well as the photovoltaic-driven electrochemical configuration. Under photoelectrochemical configurations, we got the conversion efficiency of about 50%, so similarly high as under the dark condition. But when we shift to this photovoltaic electrochemical configurations, we have lower conversions of only about 10%. And we attributed this to higher hydrogen bubble production because we operate at higher current density over here, and bubble management and is therefore shown to be very important in order to control this coupling efficiency. So we're happy with the proof of concept, and now we also want to know whether it makes sense, right? So at the beginning, I came with the premise that it would actually increase the competitiveness of the hydrogen production. So we went ahead and did a net energy and technoeconomic assessment of this concept. So Xin Yi is a PhD student in my group, and Chen Shuo was a master student that also helped with this project. So we look at the system boundary of our process, and we look at the cradle to gate and the device level analysis. The result is shown over here first for the energy balance. What we show in this table is that the cogeneration of MSA improves the energy balance of the system. So we take an example here for a device with a solar to hydrogen efficiency of 5% and a longevity of 10 years. If we first consider no production of MSA, right, i.e. this is just a hydrogen production device, we actually have a negative net energy balance of about negative 160 megajoules per meter square per year. What it means is that the energy output that we produce throughout the 10 years cannot compensate the energy input that we put to actually build the system. However, if we just introduce a little bit of a hydrogen to MSA conversion of just 2%, we can actually achieve the net energy balance over here of 0. And of course, as we increase this hydrogen to MSA conversion efficiency, which we can already demonstrated in the previous slide, we can actually achieve a more positive and much more favorable net energy balance. The same is the case for the technoeconomic assessment, right? So cogenerations of MSA also decreases the LCOH. So this table over here is the results of our study. It's summary, where we compare different hydrogen production technology, right, from a particular report here that we cite, and we compare it with our coupled concept. And this analysis shows that if you actually have a solar to hydrogen efficiency of 10%, and you can transform or at least use 8% of your hydrogen to do this coupled hydrogenation concept, we can actually arrive at the LCOH of hydrogen that is very much competitive with the hydrogen produced even with a fossil fuel-based approach. So this feasibility study actually provides us motivations to actually try to pursue this approach. Okay, with that, I think I arrive at the end of my time, allocated here. So I'll end with a summary. So first, I introduced a scale-up, showed additional losses that we need to understand and consider because improper cell design results in a very significant voltage loss. pH gradients is shown to be significant, both through simulations and experiment. I don't show today in the case of highly acidic pH, but we also did simulated this and studied this with increasing size, and it turns out to be non-negligible as well, even in a highly acidic pH. Natural convection, be it due to density change or bubble formations, needs to be exploited. Bubble crossover is a dominant factor under tilted orientations, and we have explored the use of porous polymer sheets. And finally, the last topic that I talked about as we proposed and introduced a coupled hydrogenation reactions using in-situ generated hydrogen in order to increase the competitiveness of green hydrogen. In this case, itaconic acid to MSA reaction is demonstrated, but of course this is just a model example. This is just an example. Other hydrogenation reactions can also be considered. Finally, I'd like to acknowledge my group, also the institute, the people that's listed down here, our collaborators, funding agencies, and of course, thank you all for your very, very kind attention. Thank you.
Thank you very much. Thank you very much, Dr. Abdi, for this very interesting talk. As Dr. Abdi will not join us for the roundtable discussion, we can start the Q&A session now. So whoever has any questions is free to ask them. And we already have one.
Hello. So a pretty simple question, I say. Regarding this scale-up problem, when you increase the electrode size, which was shown in the example of bismuth vanadate, would it be possible somehow to kind of, by changing the shape of the electrode, instead of having a rectangle, making something kind of more exotic, would that potentially mitigate this scale-up problem? Thanks.
Yeah, thank you very much for the question. Yes, this is also, of course, a factor. So we are looking into. There's a couple of other suggestions that are actually placed in the literature regarding the device designs, and of course the scale. This would very much impact it, because even the axis of the scale is also impacting as much, right? For example, the axis in the directions of the illuminations is probably, the directions of the flow probably is affecting less as in comparisons to the one that is perpendicular to the flow. Yes, of course, and other factors such as the rectangular, whether or another type of course going to impact it a lot, and I think this is something that we just need to explore. The other thing that I want to also mention is that so far, I think in my talk I show one scaling strategy, which is really to scale up the area, right? But another scaling strategy is of course to increase the power by increasing concentrations, and you could also scale up production by increasing input with concentrations, and I believe Sophia probably will talk about it later, and this could be another way to prevent any areal specific loss mechanism, to minimize any areal specific loss mechanism. I hope that answers the questions a little bit.
Questions? Okay, we have another question.
Hello. Photoelectrode efficiency decreases when you increase the photoelectrode area.
I'm sorry, the question was it was interrupted at the beginning, and I couldn't catch the beginning.
The question. So you showed nicely that the photoelectrode efficiency decreased as you increased the photoelectrode area. What happens if you go smaller than 0.3 centimeters square? Can we actually see higher efficiencies, or are we already at the sort of highest we can get intrinsically from a bismuth vanadate material?
Yeah, so we we went slightly lower, I think, but it's already plateauing. So I didn't show here, but we also go from 0.3 to a little bit larger than that. So we have a little bit of intermediate points, and at about 0.5 to 1 centimeter square, the value is already the same as 0.3. I think that's already saturating, and the impact of these three distributions, three different contributions, I think it's no longer limiting the performance, and now really the performance is limited by the bismuth vanadate itself, and therefore there's no impact as going to lower area. I hope that answers the questions.
Any other questions? Okay, so I guess this is it. Thank you very much again for attending our event.
Thank you very much.
The presentation was very interesting and quite enlightening for us young scientists. We hope we can see you in the future.
Yeah, thank you very much.
Thanks again.
Thank you. Bye-bye.